When we found the Schwarzschild solution, we immediately noticed that the metric has two singularities. Let us start by rewriting the metric in the way in which we are going to use it in this lecture. Okay, we are not going to use the angular part a lot, but you know that it is given by d theta squared plus sine squared theta d phi squared. And the most important thing is that lambda, this function here, is given by 1 minus rs divided by r. The actual value of rs, which is 2gm in units of c equal 1, will not matter too much in this discussion. So the singularities that we noticed were at r equals 0, because clearly lambda diverges at that point, but also this part of the metric becomes 0, and also at r equal to rs, because now this component is 0, but this one blows up. Okay, this is the most problematic thing, that one of the components of the metric diverges. So we want to study in this section and in this video what is the nature of these two singularities. This one is very similar to the singularity that you have in the Coulomb field, for instance, and we expect it to be a physical singularity. So how we have related this metric to this solution corresponding to the gravitational field produced by a point particle. Okay? It doesn't have to be like that, but it makes you think of that situation, and then it is understandable that the gravitational field is singular at r equals 0, okay, which we still haven't proven, but it smells a bit like that. Okay, but we have to discuss what we mean by divergence. In the case of the Maxwell field, in particular of the Coulomb solution, what we have is that this component of the electromagnetic two-form is, okay, I don't care very much about the units, is something like this, is proportional to 1 over r squared, which clearly diverges at r equal to 0. Well, in this case, this is gauge invariant. Okay, so we could have started with the potential and said that if you write the potential like this, okay, and it looks singular, you still don't know, because you could add to it some other function by a gauge transformation, so you may remove the singularity. However, once you have computed the field strength, which is gauge invariant, this is not possible anymore. The only thing that remains to be seen is if this was some kind of coordinate effect. In order to see if the singularity is or not a coordinate effect, you compute things which are coordinate independent, like invariants. For instance, f squared. F squared, which, okay, we are working in Minkowski spacetime, will be minus ftr squared, which is something of this kind. Okay, now this, the value of f squared, which is a scalar, is a coordinate invariant, does not depend on the coordinates. The particular expression does depend on the coordinates, but the fact that this diverges at r equals 0 cannot be avoided no matter how you change the coordinates. And then we know that there is a physical singularity there. In general relativity, if you translate this discussion to general relativity, then it looks like you should study the invariants constructed from the Riemann tensor. Okay, things like r mu nu rho sigma, r mu nu rho sigma. Of course, you could have started with just r, the rich scalar. Okay, but in this particular case, r is 0, okay, for the Schwarzschild solution, because the Schwarzschild solution satisfies that r mu nu is equal to 0, and then the trace which is the Ricci scalar is 0. So this one doesn't diverge, but then it seems that you may find something which is different from 0 and may diverge or not by looking at these components of the curvature. This is something that we are going to do. When this scale curvature invariants diverge, you say that you have a curvature singularity, which is clearly a physical singularity. And therefore, this kind of singularities are physical because they cannot be removed by a change of coordinates, according to this discussion. Okay, so what other kinds of singularities can you have? Well, a possibility is that the singularities that we have at r equals 0 or r equals s are coordinate singularities. These are singularities which obey to the fact that the coordinates that we have introduced fail at a point to be good coordinates. The main example would be that of the Schwarzschild, of the Minkowski metric, which has this completely regular form in Cartesian coordinates. It is regular because it is invertible, all the components are constant, there is no problem whatsoever with it. But if you rewrite it in spherical coordinates, what you find is the x0 squared minus the r squared minus r squared d omega squared, and clearly at the origin at r equals 0, the metric is singular, the determinant is 0, and it cannot be inverted. In fact, the change of coordinates from x1, x2, x3 to r theta phi is not invertible. A single point, the single point x equal x1 equal 2, x2 equal x3, which is the origin, corresponds to an infinite number of coordinates values in the spherical coordinates. So it would be r equal to 0 and arbitrary values of theta and phi. There's another way of seeing that the change of coordinates is not good. But if we had started from the beginning with this form of the metric, we could have concluded that there is a singularity, and then the only way to prove that the metric is indeed regular would be to find the change of coordinates to coordinates, to Cartesian coordinates, because then you prove that the metric is indeed regular. You have to show that the new coordinates cover exactly the same patch that the original ones. In this case, in this hypothetical case, this could be these spherical coordinates. They cover everything except the origin, which is not where it is not regular. Then you change to this, they cover also everything but also the origin. A possible situation is that your coordinates are good in some region. Okay, you may have some singularity over here. Okay, your coordinates are good in all this region, and then when you switch to some other set of coordinates, okay, this is a change of coordinates, so there must be at least an overlap in this region with the new coordinates. But sometimes these coordinates are good in a larger region, okay, which includes this place. Then you have proven two things. Okay, if the new coordinates are also regular here, you have proven that the metric was already regular here, that there was a problem with the original coordinates, but you also have extended the metric. This is called an analytical extension. Your space-time is larger than you thought, because when you were moving in this direction, you just crashed against this coordinate singularity, and then you don't know what happens beyond that, or you cannot be sure that what lies beyond that is regular space-time, until the moment in which you prove that, okay, this was just a problem with these coordinates, and there are other coordinates which really allows us to go beyond this. Okay, so this is something that we can also find. Even if you if there are no curvature singularities, suppose that you find some other coordinates and it doesn't look like there is a curvature singularity, there is another possibility of for a space-time to be singular, or a metric to be singular, and this is that you follow the geodesic of a particle, and for a finite value of the affine parameter, it stops at some point, and you cannot extend it anymore. When this happens, then you say that the space is geodesically incomplete, and clearly there is a singularity of some kind there, which doesn't have to be a curvature singularity, but it's still physical because it affects the motion of particles. Okay, so this is the third possibility. So what we are going to do to summarize is, first of all, we will investigate the curvature invariance of the Schwarzschild metric, and then we will study the geodesics. In particular, we will study the null geodesics, and we will focus only on the radial null geodesics, which are those which have theta and phi constant and are directed towards r equals 0 or from or come from r equals 0 towards r equal infinity. There's another question that I'm not going to study, but that you can look in the gravitation book by Misner, Thorne, and Wheeler, which is the finiteness of the components of the Riemann tensor. They appear in the geodesic equation contracted with tangent vectors to geodesics and to the deviation vector. So at least part of this equation is really coordinate invariant, and this kind of calculation gives you an idea of the forces, of the tidal forces that suffer the objects that are moving in a certain geometry. Here this would be the Schwarzschild geometry, and you can consider not just points but objects, really extended objects, okay, using this deviation vector, and see what are the stresses that these objects suffer. They are idealized as, for instance, 2 points, okay, connected by this deviation vector, and which are pulled or stretched or whatever by the tidal forces. You can look at at this book where this is computed and estimated for the fall of a human in the Schwarzschild geometry. As we have mentioned, many of the curvature invariants of the Schwarzschild metric vanish because the Schwarzschild metric is a solution of r mu nu equal to 0. So, for instance, r mu nu, which is very simple, or r are both 0. Okay, you have to look for other invariants which are more complicated to compute. The ones that are usually computed are the Riemann invariant, and this one gives you 48 m squared cosine squared theta divided by r6 plus other terms which we do not care very much about. The important thing about this is that you see that there is really a divergence at r equals 0, a very strong divergence. Other invariants that one can compute are this is the Riemann, then there is the Chern invariant, in which you contract r mu nu, but then you have alpha, beta, gamma, delta, and this is contracted with alpha, beta, gamma, delta. And then the Euler invariant, which you have probably met when if you did this or tried to do this exercise on the Gauss-Bonnet Lagrangian density. So this is r mu nu, alpha, beta, r rho sigma, gamma, delta, and then epsilon mu nu, rho sigma, and epsilon alpha, beta, gamma, delta. So you contract with epsilon this, and then with the other epsilon this and this. Okay, it is enough that one of them diverges to show that this the singularity at r equals 0 is a physical singularity, because it is a curvature singularity. Then you have to compute all the rest in order to see if there is a divergence at r equal rs at the Schwarzschild radius. Well, if you compute the rest, all the possible invariants, and this is a very delicate problem because not all of them are independent and there are quite a few, you see that there is no curvature singularity at r equal rs. In fact, the best way to show this is by proving that this is indeed a coordinate singularity. Because if it is a coordinate singularity, we will, by a change of coordinates, convert the metric into a metric which is regular at r equal rs. If the metric is regular, the curvature will be also regular there. When we studied geodesic motion in the Schwarzschild geometry, we studied in particular the case of massive particles in radial motion directed towards r equals 0. But we called at the time a radial plunge. And we computed the proper time that the observer would measure, that it would take him to, or her, to arrive to the surface r equal rs, where this Schwarzschild singularity is placed. And we found the somewhat surprising result that this time was finite. The actual value is not important. It's just that this is an indication that in principle this point, or this surface r equal to rs, is an ordinary point, that the apparent singularity is due to a bad choice of coordinates. We will not dwell on this point anymore, and we will move to the next item, or the next section in this lecture, which is the study of alternative coordinate systems in which this singularity disappears. In fact, these coordinate systems are based, or are related to the motion of particles, not observers anymore, because we will consider massless particles, but the idea is basically the same. Okay? We are going to use these world lines, the world lines of massless particles, as coordinate axes. And if these world lines are regular, then we will have found coordinates that are regular also at that point. We're going to see that, and the fact that these coordinates are not just regular on that point, but beyond that point. And we will have then extended analytically this exterior Schwarzschild geometry, because to this point we can only trust it from r equal to infinity to r equal to rs. To understand a bit better what we are going to do, let's start with a non-relativistic example. Okay, although I am going to draw this space-time coordinate system in the standard relativistic way, in which time grows upwards. This is supposed to be a non-relativistic example, and let me consider the paths of these are not exactly world lines, the trajectories of particles moving at the speed v. They are given by these equations, where x0 is the initial time and v is the speed. Okay, so I am just going to use two kinds of speed, +1 and -1 in whatever units this is done. Okay, so I am going to consider these trajectories, and these ones. Okay, I can write this combination is always going to be the constant x0, and here this combination is always going to be this constant x0, the initial position, which is the integration constant here. Now let me draw them. Okay, So these lines, they cross the point x0. They have a slope 1, just by convention. Again, in whatever units, this doesn't have to be the speed of light. And they are like this. So as I let x0 vary, I get these lines. Okay. So these are, we can write this as x minus t equal to x0, just to remind ourselves what these lines are. They are directed this way if t moves forward. And the other ones are, on the contrary, they also go by x0. Oops. They also cross the index, the axis x at x0, and if we let x0 change, we get these lines. Okay, if you want, they are directed in this direction. Okay, so now the idea is to use this integration constant as a way to label the axis and then as a coordinate. So I'm going to call this combination x minus t, I will call it minus u, and x plus t, I will call it v. Okay, I have used the same conventions as I am going to use in the relativistic example of the relativistic case. So, well, you see that these lines have different values of u, and therefore they are measured, okay, or they are distinguished by the values of this orthogonal axis. So this will be u, okay, different values of u label these different lines, okay, this one, and so on. They are characterized by this u. And different values of this axis, okay, probably I can use any axis at any point, okay, but typically use them, use the one that crosses the origin of coordinates, but it doesn't really matter. Let's take any one. So for instance, this one, different values along this axis labels these other lines. So this is what you would call v. Okay, I think I am using not capital letters. Again, u. Okay, so this is the idea. This will be the u axis. It labels really the lines which are orthogonal to it. In this case, they are straight lines. This will be the v-axis. It labels the lines which are orthogonal to it. And the relation with the coordinates is given by, with the all coordinates, is given by these two expressions. And this is how we are using coordinates associated to the motion of particles. Okay, these are particles with given speeds, positive and negative, and distinguished by the value of the initial position. So if we have an infinite number of particles, we cover all the possible values of x0. We need a set with positive velocity and another one with negative velocity. So those that when t grows, okay, in this case, when t grows, x has to grow also. So, and it is in this way that x0 remains constant, and this means that these are directed towards, well, when t always evolves to greater values, this means that these particles are always directed in this direction, in the direction of growing x. Okay, we will call this kind of lines or motion outgoing. Okay, because in the case that we are going to consider, the inside, okay, will be in this direction for smaller values of x, which will be smaller values of r. And in the other case, when t grows, x has to decrease to keep this value x0, whatever it is, constant. So these lines with characterized by v, the coordinate v, will become incoming, okay, and they are directed towards decreasing values of x. Now let's move to the case of interest. We are going to study the motion of massless particles or light rays in the Schwarzschild geometry. We are going to study only radial motion. We know that this motion is determined by the geodesic equations. We have seen all this, but I will just remind you how it works. With an additional condition, x dot mu x dot nu equal to 0, that tells you that the geodesics are null geodesics or light-like geodesics. This equation assumes that the parameter that we are going to use is the affine parameter, and we are going to call it psi. Well, the geodesic equations, we wrote them, we have written them many times. There is one for each coordinate, okay, t double dot, now we'll write them, r double dot, and theta double dot, and phi double dot. Now the one thing that you have to know is that these two equations for the radial motion case, which is the case in which theta is constant and phi is constant, these two angles determine the direction, the angle with which the particle goes to r equals 0, and these angles are constant, then these two equations are satisfied, okay? So we are not going to need them anymore. And finally, the null condition, which is just g00, which we call it lambda t dot square minus g or plus drr, which is minus 1 over lambda r dot square. Okay, and this has to be 0. Okay, now let me write these geodesic equations. There are only a few non-vanishing Christoffel components of the Christoffel symbols with t up and so on. In this case, the only one which is different from 0 is tr, and because it is off diagonal, it appears twice. Okay, so this is equal to 0. And for r double dot, also taking into account that theta dot and phi dot are 0, there are only two components also that are different from 0. So it's gamma ttr and gamma rrr square equal to 0. Okay, these are the three equations that we need to solve, and we just use the components that we have computed already in the past. So with this factor of 2, what you get here is lambda minus 1 lambda prime, and here it is a half of lambda prime, and these three r's is minus a half of lambda minus 1 lambda prime. Well, remember that this equation, okay, can be written in this way. So lambda lambda prime is d lambda over dr. This is r dot is dr over d psi. So this is the psi of lambda, and t dot, if I take this factor of 1 over lambda as a common factor, okay, and this is equal to 0. So if you want, I multiply everything by lambda, you get this expression, and then this expression was equal to d lambda t dot d psi equal to 0. This was the expression that of the fact that lambda t dot is a conserved quantity that I am going to call epsilon. So the conclusion is that t dot is epsilon divided by lambda. Okay, and this is one of the equations that we have to integrate. Okay. Now we can use this equation here to simplify this one, because you see that this becomes r double dot plus a half that we take as common factor. Lambda prime is also a common factor, and then you have lambda t dot squared minus lambda minus 1 r dot squared equal to 0. But using this equation, we know that this cancels, this is 0, and the equation becomes r double dot equal to 0. Okay, so this is basically all we have to do. Okay, and we integrate first r double dot equal to 0, which means that r is a linear function of psi. We can always eliminate this b by shifting psi, so just ignore it. This means that if the initial r has a finite value, then psi will start with a finite value, but this is not really a problem of principle, and we will take this to be the solution without any loss of generality. This choice of b equal to 0 simplifies our life. Now you can go to the equation for time, because you have the psi equal to epsilon over lambda. Lambda is 1 minus rs divided by r, but r is a psi. This means that we can integrate it. This is just a function of psi. So, as usual, we do this, and we are going to integrate it. But see that if I multiply and divide this by a, okay, or if I multiply both terms by a, which is equivalent, let me also divide by epsilon. Okay, what I have here is the of a psi, and really this is the r over lambda of r. Okay, so I can rewrite my integral in terms of the new variable or the old variable r. We can integrate both sides, and this integral, which is 1 minus rs divided by r, the r, what I do is I multiply numerator and denominator by r, then I subtract and add rs, okay, everything times the r, and this is clearly 1 plus rs divided by r minus rs, the r, which gives me r plus rs, the log of absolute value of r minus rs, plus an integration constant, which I am going to change several times. On the other hand, this gives me a divided by epsilon t. Now first I want to have something which is dimensionless in the logarithm, so I would split this, well, this constant would be rs times or minus rs, the logarithm of rs, which means that I just divide everything by S. Here, this would be C prime, but let's not worry too much about that. And okay, this is the solution. Let me just say a few things about this solution. This combination is usually called the Tortoise coordinate. Okay, and it is called. It is denoted by R star. The definition of this coordinate. Okay, well, it is this integral, but just look here, the main property, okay, because this is the result of having integrated this expression. This means that dr divided by lambda is dr star, and this is the definition of the tortoise coordinate. This definition has the following property, that if the metric has this form, divided by lambda minus r squared d omega squared, then you see that if I multiply and divide by lambda, or let me do it in another way, this, if I take lambda as a common factor, I have dr squared over lambda, or dr over lambda squared, and I apply this definition, then the main property of r star is that in those coordinates the metric has this form, and this tr part of the metric is conformally flat. Okay, it is conformal. This means that there is a rescaling of the metric, which would be a rescaling by this parameter that brings the metric, or the inverse, that brings the metric into the flat form, which would be this one. Okay, I am ignoring the angular part because it doesn't play any role. This form of the metric, on the other hand, is something that you have to get used to. Sometimes you write things like this. This implicitly means that the metric, the coordinates that you are using in this metric are r star, theta, and phi. So if you see r here, it means that r has to be taken or considered as a function of r star. Which function? Well, it is determined by this equation, which in this particular case has this form. We will see other metrics, okay, like the Reisner-Nordstrom metric, in which you can play exactly the same trick, and you can find, well, a bit more complicated form for this r star, but you can still find it. Okay, and the same with lambda. Lambda is a function of r, which is itself a function of r star. But sometimes this is not completely spelled out explicitly, and the metric is written like this, and this means that your coordinates are t, r star, theta, and phi. Okay, and if you see something else that looks like a coordinate, it has to be understood as a function of the new coordinate that appears here. Okay, so let me remove this because this is just an aside. Okay, although it's important, we will use this later. What we have obtained is this relation t. Let me multiply everything by epsilon a now. So I write minus epsilon divided by a r star equal to c, which again is a new constant. I just rescale it. Since I don't know what it is, it doesn't really matter. And this expression should remind you of the example that we studied here. Okay, maybe the order in x and t is not the same, but the spirit is certainly the same. Okay, these are the implicit forms of the null radial geodesics in Schwarzschild space-time. Okay, here this is to be understood as a function of r, this function which is written at there. And the idea is that we will take two sets of null radial geodesics. Some of them will be directed towards growing values of r, and some of them directed to decreasing values of r. We will call them outgoing and ingoing. and we will use this integration constant to characterize them, and they will be this integration constant will be promoted to the new coordinate, and we will have two new coordinates depending on whether we consider ingoing or outgoing geodesics. Observe that when r goes to infinity, okay, r star goes to infinity. So growing r means growing r star, at least in the exterior part of the geometry. Then, motivated by the example and so on, if you study ingoing light rays, okay, ingoing means that r dot has to decrease, okay. Basically, if psi is the evolution parameter, it is the affine parameter. When psi grows, t has to grow, and if this light ray is ingoing, it goes to smaller values of r, then the derivative of r with respect to psi has to decrease. But remember that r dot is a, which means that this a has to be negative. In this case, we are going to choose this parameter epsilon such that minus epsilon divided by a is equal to 1. And with this choice, you have this relation, and this, okay, which in originally is just the integration constant, and we are going to use as the coordinate v. Okay, it is the fact that it is a null coordinate. Well, I will explain it in a second. Okay, so now we have the outgoing. Outgoing are characterized by a positive derivative of r dot, which means that a has to be positive, and in this case what we choose is minus epsilon divided by a equal to minus 1. Okay, it's a choice of epsilon. Epsilon, you take it to be positive, at least in the exterior of the Schwarzschild geometry. Exterior meaning r larger than rs, where lambda is positive. Because then, if lambda is positive, you want t dot to be positive, because you want t to grow when psi, the evolution parameter, grows. This means that you want epsilon to be positive. Okay, and you see that in these two choices, okay, a is negative, but there is this minus here, so epsilon is positive, and that's okay. And here also epsilon is positive, because now a is positive. So these choices are perfectly correct. And in this case, you have t minus r star, which I am going to define as u. Okay. In the past we had minus u, and that was because the order of these coordinates was reversed. Okay. U and v are known as the well, incoming and outgoing Eddington Finkelstein coordinates. Okay, well, maybe before I go on, we can tell a bit the story of these coordinates, and of these are, if you want, the first coordinates that show, as we are going to see, that at r equal to rs there is no physical singularity, that the metric is completely regular. They were first discovered by Eddington, but it seems that Eddington did not realize the implications. And later they were rediscovered by Finkelstein. Still, historically, it was Lemaitre who first realized that there was a change of coordinates that could make the Schwarzschild metric regular at r equal rs. Lemaitre is probably one of the best early relativists. He was the first to observe the the fact that galaxies had an apparent motion of going farther away from us, and that they were going faster the farther they were from us. So that was the Hubble law, and this was before Hubble. He also realized that the Schwarzschild solution was regular at r equal rs, that it was just a problem of a bad choice of coordinates. Now this looks simple, but at the time this was not an easy thing to realize. It took a lot of years. And Le Metric was also the first to propose the Big Bang. Okay, so this is just a historical aside. Okay, now, why are they null coordinates? If I use both of them, you see that it's very easy to see that dt squared minus dr squared is du dv, okay, which is the standard expression that the metric has in null coordinates. And, well, it is understandable because they characterize null geodesics. Now, the next thing that we are going to do is to really write the metric in incoming or outgoing Eddington-Finkelstein coordinates. But this is not writing the metric using both u and v at the same time. So incoming means replacing t. So we have the original coordinates. So you replace t by v, and outgoing you just replace t by u. Okay, and you keep the coordinate r. This is important. And this is easy to do. Using these expressions, you find that t is v minus r star, or that t is equal to v plus r star. So that dt is dv minus dr star, or in the other case, this is du plus dr star. Now, let's go, well, we use this fundamental property that dr star is dr over lambda. Okay, and now we go to the Schwarzschild metric, and we have lambda that multiplies dt squared minus 2dr dv divided by lambda, and plus dr squared divided by lambda, lambda squared, minus dr squared divided by lambda minus the angular part. Okay, and you see that these two terms cancel, and that you have a metric which has the form lambda dv squared minus 2 dr dv. This goes away, and then the angular part. And here it is pretty similar, except for this sign, okay, which is what distinguishes incoming and outgoing radial coordinates. Finkelstein, Eddington-Finkelstein coordinates. And minus r squared d omega squared. Okay. Okay, and now you'll say, okay, but you have not eliminated this problem here. You still have lambda, and this lambda will vanish at r equal to capital Rs at the Schwarzschild radius. But when that happens, you see that the metric has this form. It is this 0. Okay, now the coordinates are v r theta phi, so this would be g vv, and indeed it vanishes at r equal rs. So let me see that r equal rs. What happens is that gvv vanishes, And then you have GRV has the value -1, and then minus r squared sine squared theta. Now you compute the determinant of this metric, and it is different from 0. Yes, because this has a determinant -1. So the metric is regular, and you can invert it there. And the same happens to this metric here. Okay, the difference is that you have 1, 1. Okay, and the same here. Now we can reconsider the problem of this of finding the null geodesics, the radially directed null geodesics in the Schwarzschild geometry, but using these coordinates, which are valid in all the range of values of R, which extends from R equals 0, where we know that there is a physical singularity, to R equal infinity. Okay, and includes R equal to Rs, which now we have seen it is a completely regular point in the geometry, although it is certainly a very peculiar point. If we want to study the problem of null geodesics, we need to compute the components of the Christoffel symbols in this new metric. Let me consider just the ingoing coordinates. Okay, so I will use this form of the metric, and well, I am going to compute just as an exercise, a simple exercise, the components of the Christoffel symbols only in the directions v and r, because for theta constant and phi constant we don't need any of the Christoffel symbols with theta or phi indices. Okay, these are the first of them would be GVV. And okay, then the first thing that you see is that you need to compute the inverse metric. Okay, it is enough to because the metric is block diagonal, we just have to invert this metric, and you can see, and this would be the corresponding block in the inverted complete metric. Okay, it is more or less trivial, all this that I am saying, and it is not difficult to see that this is 0, -1, -1, and lambda. Yeah, I mean minus lambda. So well, let's go back here. This is 2 times dv gv mu minus d mu gvv, and well, gvv with indices up is 0. Okay, this is gvv. So the only possibility that you have is the off diagonal GVR to get something different from 0. And if this is R, okay, and this is R, okay, GVR with indices down is constant, so this vanishes, and this is -1 GVR with indices up, which is -1. So minus and minus is plus. Okay, this half, and GVV with indices down, which is lambda. Okay, with the time with the derivative with respect to r. So this is gamma VVV. Next, we have to compute gamma VVR. This is GR mu, and again 2 times delta VGV mu minus mu GVV. The only possibility that will give you something different from 0 is GRR, so mu has to be R, because the other possibility is GRV, but if this is V, there are basically nothing depends on v, so this is going to vanish, and GVV is a function of r only, so the only possibility is that this is GRR. Okay, so this is a half. GRR with indices up is minus lambda, with this minus and minus is plus, so this is just lambda, and then we have the derivative of GVV, which is lambda prime. Okay, so the result is that, maybe we collect them here, this is a half of lambda prime. Okay, the next component is VRV, and this is the V mu, and we have partial mu, GR mu partial R, GV mu minus partial mu GRV. GRV is constant, so this term is not there. And now mu can be either v. If it is v, well, this is a partial derivative with respect to v, it doesn't contribute. So let's look here. If mu is r, then we have GVR, which is constant, and we get nothing, so mu has to be v. That's the only possibility of getting something different from 0. Okay, but GVV is 0, so this component vanishes. The other component that we can consider here is GRR. So partial V, R mu plus partial R, G V mu minus partial mu, GVR. Again, this term cancels for the same reason, because it is constant. This term because nothing depends on v. And here we know that mu has to be v in order to get something different from 0. Okay, GRR is minus lambda, and GVV is lambda prime. So this is GVRR is minus half lambda prime. Next we have to compute this one, V mu. Now this comes twice minus the mu GRR. The mu GRR is 0, always, because GRR is 0 in these coordinates, and GR mu, if mu is r, again this is 0. If mu is v, this is also 0, because this is the derivative of a constant, so this is 0. And okay, the point is that here we get the same thing, and this was 0 by itself. Okay, there was no way this was not 0, so this is going to be 0, and we arrive only to these 3 non-vanishing components of the Christoffel symbols. Then the geodesic equations will be well, with an index v upstairs, there is only one. That gives us lambda prime, and then v dot square, this has to be 0. Then with an index up, there are 2 terms. One of them is this, lambda prime v dot square, and the other one is minus a half lambda prime r dot square equal to 0, and the mass shell condition, which in this case is, well, you read it from here, it is lambda v dot square minus 2 r dot v dot. So it's lambda v dot square minus 2 r dot square v dot equal to 0. These are the three equations, and this equation can be written taking v dot as a common factor. And I know that the same should happen here. Then I realize that I have made several mistakes. Okay, one of them is that this corresponds to VR. So instead of minus 1/2, I should have just minus, and instead of r dot square, I should have r dot v dot. But if I take a common factor lambda, I don't get this, which I should also get, which takes me to the fact that I have also made a mistake here, because when I replace v here, I put the r here. It should be rv. Okay, this means that this is just lambda prime and here this is just lambda prime. And if I take okay, lambda prime and v dot as a common factor, then I get lambda v dot minus minus 2 r dot. Okay, here I have forgotten also a v dot from the square. Okay, sorry for all the mistakes. The important thing is that in the end the result is correct. Okay, so you see that there are two possible ways of solving this equation, but in any case, if you so v dot can be 0 or lambda v dot minus 2r dot is equal to 0. In any case, you have both possibilities here, and clearly this term vanishes, and again the solutions are equal to a psi. This doesn't change. And well, depending on which case you are considering, okay, you are going to solve the first equation in different ways. But let's consider these two cases separately. Okay, v dot equal to 0, which is one of the possibilities. The solution clearly is v, a linear function, a constant. Remembering what was the definition of v, which was t plus r star, this means that t plus r star was a constant. These are the incoming geodesics, no geodesics, always radial. Basically the fact that they are characterized by a constant value of v. If this is the v-axis, for each of these constant values you have geodesics that go towards smaller values of r star. This is the idea. Now the other solution, okay, let me also mention that for v dot equal to 0, this solution, which is the one we haven't considered yet, is automatically solved. The other solution of the max shell condition is lambda v dot minus 2 r dot equal to 0. Let me put this in the form v dot minus 2 r dot divided by lambda and equal to 0. And if I multiply all this by d psi, okay, this becomes this dv and dr. But remember that dr over lambda was the very definition of dr star. So if dv is dt plus dr star, then with minus 2 dr star equal to 0, what you have is t minus r star equal to constant, and these are the outgoing null geodesics. Okay, and okay, the situation is reversed with respect to the ones I have drawn here. Now let us look more closely to these outgoing null geodesics. Outgoing have r larger than 0, so r grows when the evolution parameter psi grows. They go in this direction, okay, and they are labeled by the value in the u-axis, but they also have a v dot positive, because, well, outgoing means that v grows, okay, when psi grows. Now if you look at this equation, well, you have the following. Well, it doesn't matter how you write it. This is positive, this is positive, this has to be positive by consistency, but this cannot be when r is smaller than rs. Okay, so for r smaller than rs, there are no outgoing null geodesics. Okay, so this means that light can go to larger values of r when you are outside of rs, but when you are inside of this region characterized by r equal to rs, light cannot go out, cannot go to larger values of r. And this is the origin of the idea of a black hole. The region r equal to rs, in this surface, divides the space into two pieces, one of which is such that it cannot communicate with the exterior. Because this situation that happens or takes place for radial geodesics, radial null geodesics, also happens when the geodesics are not radial. If we let theta and phi vary, you get exactly the same result, that it is impossible to have outgoing null geodesics, and it also happens for time-like geodesics. So r equal to rs is a sort of barrier for communication. Okay, always in the direction from r smaller to rs to this region, which is the asymptotic region where observers are. Okay, we never worried too much about this when we studied the tests of general relativity, because for most astrophysical objects, the surface of the planets or stars or whatever is always larger than rs. Rs is very small for any object. I mean, for the Earth is just a few centimeters. Okay, so the surface always lies beyond this surface. But you can think of what happens when there is a gravitational collapse and the object shrinks, okay, and starts shrinking, and the surface eventually crosses this r equal to rs, barrier, which is, as you know, called the event horizon. When this happens, well, you have to consider, you have to take seriously all the phenomena that take place in this region, okay, because now this region is accessible for you. It is not, there is not a planet in the middle, okay. And we are going to study much more about this in the next lecture. Okay, for the moment we will just leave it here. The problem with this exercise that we have performed is that it is difficult to visualize the whole, what is the situation in the whole space-time. We know this coordinate r, and we know that okay, this r equal to rs divides space-time into regions, but we still don't know if there is, I don't know, some way there is this barrier, and maybe you can do something like this or something like this. There is some shortcut that allows you to escape. Okay, the only way to know if this barrier is really there is to find what is the complete space-time, to find the maximal analytical extension. And we have found an analytical extension from r larger than rs to r smaller than rs. So we have extended the space-time that originally we had, which was, seriously, we could only consider this part. But we want to find what is the maximal possible extension that you can find.